All right, welcome to the online causal inference seminar. Today we're excited to have Nathan Kallus and Xiaojie Mao from Cornell talk about localized debiased machine learning, efficient inference on quantile treatment effects and beyond. So in Q&A we have a collaborator Masatoshi Uehara, but Nathan Kallus and Xiaojie Mao will also stop in the middle to take some questions, so please submit some. And after the talk, we will have a discussion by Alexandre Belloni. And after that, if we have some time left, we will take some more questions. Today, questions will be handled by Michael. So I'm going to switch to him over now.
Thanks, Dominic. So we have 3 people with us today. So hopefully we can answer all Q&A. So please submit all your questions. Keep in mind that they may be displayed publicly, and if we want you to ask your question live, we'll reach out to you and ask you to raise your hand. So with that, I'll hand it over to Nathan. Nathan, you can begin whenever you're ready.
Okay. Thank you. So continue. So I have to share my screen. Okay. Can everybody see my screen? Yeah.
Yes.
Yes. Okay. Sorry. Okay. Thank you for the introduction and thank you for the invitation. It's a real pleasure to be here. So Xiaojie and I will be talking about work that's also joined with Masa, who's here also answering questions. And it's about a new methodology that we are calling localized debiased machine learning. And as our subtitle, efficient inference on quantile treatment effects and beyond, is alluding to, one of the primary applications of our new methodology is for quantile treatment effect estimation. Now, before I try and tell you a little bit about why we should care about quantiles, I just want to start by advertising that Xiaojie is actually on the market this year. So if you're hiring, I cannot recommend him strongly enough, and you should look him up. And the other work he's done some fantastic work. So now, without further ado, why should we even care about quantile treatment effects? And that should motivate our methodology, LDML. So to motivate this, consider a hypothetical new program where we take everybody nationwide in high school, and we're going to teach them some basic computer and Microsoft Office skills. So now, in addition to all the other qualifications they now also have qualifications necessary to gain access to a pool of low-level office jobs that, let's suppose, are in demand, probably not right now in the pandemic economy, but hopefully in the near future. And then as the central question in program evaluation is, well, what is the effect of this program? What is the effect of this program on individuals' income, for example? So suppose you do an analysis and you figure out that the difference in the average income of an individual that was exposed to this program and was not exposed to this program, on average, their income increases by 0.1%, which is something, but it seems pretty small. Well, what's probably contributing to the small increase in average is that most of the income dollars in the pool of aggregate income is mostly being controlled by top earners who are getting, very high earning jobs regardless of this intervention. So they're unaffected, and that's where most of the dollars are coming from. But if we look at the distribution of incomes when we give the program, when we don't give the program, it's plausible that we could see a very strong effect in the first quartile of income because we're looking at these low-level jobs. So what's happening here, as is very well known, something like income is a very skewed distribution, and in such situations, quantiles can be much more informative than averages. Okay, so just to, in a picture, explain what is a quantile effect. So here we're going to use the formalism of potential outcomes. So we can consider the distribution of the control potential outcomes, or the distribution of incomes if nobody got this program, and the distribution of incomes if everybody got this program. Okay, and that would have 2 different distributions, which can be described by a CDF. So we have the blue CDF and the orange CDF. When we are asking what is the quantile treatment effect at level 75%, we're asking, if we make a line at 75%, where does it intersect each one of these CDFs? And what is the horizontal distance between these 2 CDFs? That is the quantile treatment effect. So this distance indicated by this dashed line is the quantile treatment effect at 75%. And this is the quantile treatment effect at 95%. And as we can see, we can really gauge how the program is affecting different quantiles of distribution, which can be very heterogeneous. So that's what a quantile treatment effect is. And just to fast forward a little bit, just to tell you what this talk is all going to be about. So it's going to be about a general methodology and the theory around it. But in terms of its impact for practitioners, for empiricists, we think that the most important takeaway from this talk will be, here's a methodology that is going to allow you to do efficient estimation of quantile treatment effects or local quantile treatment effects if you're thinking about estimating them using instrumental variables. And doing this in the presence of very high dimensional controls or otherwise high dimensional nuisances, when we are going to use just black box machine learning methods for supervised regression and some very lax assumptions. So when I say supervised regression, I mean you get data on covariates and labels. So you get n pairs of such data points, and you have some black box that's going to estimate the conditional expectation of the label given the covariate. So here, the label can be binary or continuous. If it's binary, this is going to be a conditional probability. So we're just going to call this kind of supervised regression black box a few times and be able to do efficient estimation and inference on QTEs and LQTs. So the main motivation is going to be QTEs, as I've mentioned. So let's start with how we might estimate them. Well, before we can think about estimating them, we have to think about identifying them from data. So what is the quantile that we're interested in? Well, the parameter that we're interested in is this parameter theta star, defined as the theta star such that if we plug it into the CDF of treatment outcomes, it's equal to gamma. Right? So gamma here is like 25% or 75%, et cetera. And we're going to assume it's unique to make things straightforward. And we can think about an analogous question for the control outcome quantile and the difference of the treated outcome and control outcome quantiles. And that's the quantile treatment effect. And these estimation questions are analogous. So just for making things simple, I'll focus on just the quantile of the treated outcome. So it wouldn't be a talk in the online causal inference seminar if I didn't mention the central problem of causal inference. So why can't we just invert the CDF and get theta star? Well, the problem is that we don't observe Y1. We don't observe counterfactual outcomes. For an individual that did not receive the program, we don't know what their outcome would have been if they did receive the program. So then we need to make assumptions in order to identify this from data. So one setting that is often considered is the setting of ignorable treatment assignment. So suppose that the data that we see, so generically in the stock Z is going to indicate a data observation. So in this case, we're going to observe a triplet of covariates X. So this can be, for example, this individual is a high school student in Florida whose parents did not graduate from college. And then we have an indicator for whether they received the treatment or not. So this is 0 or 1. And then we have the outcome, which is their income down the line. And one identifying condition would be to assume that the treatment is ignorable, so that potential outcomes are independent of the treatment given covariates, and that we have overlap. So for every level of the covariates, each treatment is possible in the data generating process. Alternatively, we can have identifying assumptions based on instrumental variable, and then we're estimating the local quantile treatment effects. We're going to mention that later, so let me for now just focus on just quantile treatment effects under ignorability. So if we make these assumptions, there's a way that we can identify theta using inverse propensity weighting. Okay, so we can formulate the following estimating equation that's going to identify theta uniquely. So here we wanted to evaluate the CDF, but we didn't know Y1. So the CDF is just the expectation of the indicator that Y smaller than or equal to theta. And we want Y1. Well, we only observe Y1 when treatment is 1. So we're going to multiply it by the indicator that treatment is 1. And we're going to upweight it by the inverse propensity. Okay, so if you take this equation and you plug in the true propensity, which we're going to call pi star. So the true propensity is the probability of being treated given covariates. And we're going to ask that the expectation of this thing, which is the CDF at theta, is going to be equal to gamma. That's going to specify what theta is. Okay, so this is a way to identify theta. And then to estimate theta, we're just going to replace expectations with empirical expectations and true propensities. This should have a star with estimated propensities, and then we solve the equation, the corresponding empirical estimating equation, and we get an estimator that I'm going to call theta hat IPW. So that's one way to estimate it. But it has problems. So on the plus side, estimating the propensity, well, that's just a standard binary regression task. So we have a whole toolbox of tools to deal with this for machine learning, whether it's random forest, lasso, neural nets, CART, BART, XGBoost, what have you. This is the central problem solved by machine learning, supervised regression. The problem is that this estimator, theta hat IPW, well, it's extremely sensitive to how this estimation of the propensities is done. So in very special hypothetical cases, if there is hypothetically some very extreme smoothness assumed on the propensities, and if the propensities are estimated by very particular sieve or kernel estimators, then in those unique settings, this estimator can be efficient. But all of that breaks down if you're going to use some black box machine learning estimator for the propensity. So generally, these machine learning estimates are going to have some bias, whether it's regularization, like in Lasso, or overparameterization, like in neural nets that are just interpolating the data. And in general, they're going to have sub-square-root-n non-parametric convergence rates. And now all of that is going to slow down theta hat IPW and make it a slowly converging and unstable estimate. What we would like is we would like to be completely insensitive to how we estimate the nuisances so that we can plug in any black box and just know that everything is going to be okay. So if you've heard before about orthogonality or debiased machine learning or double robustness, maybe those are the kind of things that come to mind when I say we want to be insensitive to how to estimate nuisances. So indeed, there's a way to fix this. So we can alternatively identify the parameter of interest theta star using the efficient estimating equation for the quantile of y1. So we can replace the estimating equation function by this alternate function psi, which has two parts. It has this first part, which uses this function mu, which is the regression of y being smaller than or equal to theta on x and t. And if you notice, if you take the expectation of mu star over x, you get the CDF of interest. So this first part is already saying CDF of theta is equal to gamma. And then we're also adding this debiasing part using IPW. So this looks familiar to those who know about W robust estimation of ATs. This is kind of the equivalent for QTEs, or here just for quantiles. And this estimating equation has a very magical and important property called Niemann orthogonality. So Niemann orthogonality is the property that this expectation over here, the estimating equation of interest, if we think about it as a function of a generic theta, a generic mu, and a generic pi, that function is going to have a zero derivative with respect to the nuisances mu and pi at the point theta star, mu star, pi star. So what does this mean? It means that if we have small errors in mu and pi, near theta star, when we're trying to solve this estimating equation, it doesn't really change a lot as we change mu a little bit near mu star or pi a little bit near pi star. So that means if we have some small errors in their estimation, that doesn't actually change the expectation too much because the derivative is zero. It doesn't really move a lot for infinitesimal changes. So that literally means that we're insensitive to errors and nuisances. So this Niemann orthogonality is an idea that has come up very often in a lot of works, and most recently in more modern literature, it's come up in works by Victor and Alex, the Discussant, who's going to speak later, and their co-authors. And they've used it in a variety of settings. And most recently, in this paper, double debiased machine learning, here we're just going to call it debiased machine learning. In this paper, Chernizhukov et al., they propose a generic way to leverage this property of Niemann orthogonality to plug in any machine learning black box estimate of nuisances. So in its simplest form, the procedure is something like this. We take all of our data and data points, and we're going to split it into two parts. Okay, we're going to call these parts folds. And then we're going to try and plug in zi to psi for every I. And now we have these nuisances mu and pi. And what we're going to do is for every zi, we're going to use nuisances that are estimated on the fold that does not contain zi. Okay, so we have mu and pi that are estimated on just the first fold and just in the second fold, and we plug them across the folds, average the size that we get over the data to get an empirical moment condition, solve it for theta, and that gives us our solution. And then what we get is, if we did this just right, we should get asymptotic behavior that's essentially akin to using the true propensity, the two nuisances. That sounds fantastic, right? You can just use machine learning, plug it in, awesome. Well, there's just one catch. It doesn't work that well here, because actually fitting mu star, we said, oh, we have to fit mu star and plug it in. Well, mu star here is a whole conditional distribution function, right? So we don't just have to learn a single conditional expectation, but we have to learn a conditional distribution given x, the whole distribution of y. So another way to look at it from the point of view of estimating regression functions, we essentially have to estimate a continuum of regression functions, one for every value of theta. So this doesn't exactly fit very nicely into standard ML supervised regression. There's kind of limited options out there of what you could use. You could use, I mean, there's stuff out there. You could use kernel weights to get a conditional distribution, or KNN weights, or you could build a neural network that outputs a mixture of 10 Gaussians, but that's pretty much it. And anything that's kind of like these flexible machine learning things is gonna be somewhat parametric or have parametric outputs like this neural net. Indeed, if you look at earlier work by Alex and co-authors, they constructed a theoretical continuum of lasso estimators, one for every theta, when they wanted to estimate QTEs using Newman orthogonality. So hypothetically, they had to construct a continuum of lassos, prove stuff about that, and then in practice, they had to discretize the range of theta. So it's not so simple to solve these QTE problems, even when you have Newman orthogonality. And just a quick note about this discretization. So we're generally okay with discretizing the vertical axis and saying, for example, we care about quantiles at level 75% and at 95%. And these are just the only quantiles we care about, just these few quantiles. It's something different to discretize the vertical axis, sorry, the horizontal axis, where then, we're discretizing the theta range, and we might not know exactly where this line is stick the CDF, because we're only evaluating the CDF up to these discretization points. And if we make the discretization points finer and finer and finer, we have to estimate more and more and more and more regressions. So just as a side note, you might recall, this didn't appear in DML when we wanted to estimate average treatment effects. Indeed, what's happening in average treatment effects and other types of average estimands, in those cases, the efficient estimating equation is linear in theta. So that means that nuisances are not going to depend on the parameters. They can just be estimated independently and plugged in, and we can solve for theta. In some sense, what's going on here is that DML with nonlinear estimating equations is just fundamentally hard. So one lens through which our work can be understood is a new way to deal with this hardness. And this also comes a lot into our theoretical analysis, which Xiaojie might touch upon, but maybe only a little bit. More importantly, I'm just going to focus on what is the method that comes out of this, and what are the things we can say for important practical problems like estimating quantiles. So the basic idea is like this. So with DML, we had to estimate a continuum of nuisances. Why? Because we didn't know what theta to use. There was a continuum of thetas. We needed the nuisances, all of them. So what if we did know? What if we did know what theta we should use to plug into that nuisance? Well, that sounds a little like a catch-22. Well, if you told me theta, I'm done. Why am I estimating nuisances? I'll just use this theta, right? That's what I want to begin with. If you get theta, why do other things? So it turns out that actually, that's not quite right. You can have a very rough initial guess, and that's enough. So for example, for QTEs, it's going to look something like this. We're going to start with a very rough initial guess. For example, theta hat IPW, which is a very rough guess because it has a slow convergence rate. And then we're going to estimate nuisances just at this point, just at theta hat IPW, not at the continuum of thetas. And then we're going to use an orthogonal estimating equation to refine this estimate and get something that is efficient. Okay, and now this estimation problem is just a single binary regression task. So what I'm going to do next is I'm going to describe the method in a bit more concrete detail and explain to you why it might work and how it works. And then I'm going to turn it over to Xiaojie, who's going to tell us more about the theoretical things that we can say about this method and its asymptotic behavior. And then we're going to talk a little bit about empirical results on estimating QTEs and LQTs, and then we're going to conclude. And before we turn to the theoretical guarantees, we're going to take some questions. So let me start by talking about the method and fleshing it out a little bit more in detail. So to understand the method, it's going to be useful to actually abstract away from the quantile estimation problem and think more generally about any estimating equation that's orthogonal. So let's suppose that we have data, z1 through zn, that is drawn IID from some distribution P. And that's going to be the data. And what we're trying to estimate or conduct inference on is a parameter theta star, a d-dimensional parameter that's defined in terms of following d-dimensional moment conditions. Okay, so it's defined by this moment being equal to 0. The moment is given by a function psi, applied to the data, applied to the parameter, and with some nuisances that define psi, where there's two types of nuisances. One nuisance that doesn't care about the estimate, it's just a function, and another nuisance that depends on the parameter of interest. Okay, so these nuisances are unknown, but they are estimable from the data. So this is going to be the condition that defines theta star. And notice we have a d-dimensional parameter defined by d-dimensional moment conditions, so we are in the just identified setting. And there's many examples that we talk about in the paper of settings like this, including estimating QTEs under ignorability, local QTEs using an instrumental variable, estimating conditional values at risk, expectiles, general estimating equations with incomplete data, etc. In all of these cases, whenever the estimate that we care about is not an average parameter, the efficient estimation equations are going to have estimate-dependent nuisances, which are going to lead us again to this problem of having to estimate a continuum of nuisances. So where should we start? How do we make progress? Let's think about first what happens if we knew what the nuisances were. So suppose we knew eta 1 star and eta 2 star exactly. Then one way to estimate theta is to replace the expectation in the moment with an empirical expectation and solve the empirical estimating equation. Okay, so let's consider this hypothetical infeasible estimator theta tilde, which solves this equation. With this expectation, En means take a sample average over the z's. This is now just a standard z estimation. So using standard results, we can understand how it behaves asymptotically. And we can see that under some lax regularity conditions, theta tilde is going to have this representation as an asymptotically linear estimator. So it's going to look like a sample average plus some vanishing noise. Okay, so in particular, it's also going to be asymptotically normal because it looks like a sample average. And its asymptotic variance is just going to be controlled by the variance of this quantity that we're taking a sample average of. Okay, this is called the influence function. So the influence function here, it consists of psi, the function that controls the estimating equation, with plugged in theta star, eta 1 star, theta star plugged into eta 1 star and eta 2 star. And then in front, we're multiplying by the inverse of the Jacobian. So this matrix J star is defined as the Jacobian of the moment condition, which is take the moment condition for generic theta, differentiated with respect to theta, and then plug in theta star. So just a reminder, right? This is an infeasible estimator. The problem is that eta 1 star and eta 2 star are actually unknown. So DML, the approach of DML was to cross-fit these estimators, these nuisances, and plug them in and solve for theta. But the problem was that that meant estimating a continuum of nuisances. So how do we make progress? Well, here's an idea. What if we change the oracle equation a little bit? So instead of thinking about psi depending on theta, both through its direct effect through the argument of theta here and through its effect via its effect on eta 1 star, let's change this into theta star. So we're going to fix the argument of eta 1 star to theta star and only solve for theta in its effect on the argument of psi. This is a different estimating equation, but it's still in this case, where we just think about these as true known quantities, is just a z estimator. So we can do the same trick and think about what its asymptotic behavior will be like. And it will also be asymptotically linear. And now the Jacobian is slightly different. So everything is the same except this J quantity. Now instead of J star, we get something called J diamond. In J diamond, all that's changed is before we take the derivative with respect to theta, we fix the effect of theta on eta 1 star at theta star, only differentiate with respect to this theta, and then plug in theta star. So there are different estimating equations. But what we're going to do is we're going to make the very convenient assumption that actually the Jacobians are exactly the same. So what this means is that these two estimating equations lead to the same asymptotic behavior. Okay, so both theta tildes would have the same asymptotic behavior. This seems like an extremely convenient and nice assumption. Next, I want to argue to you that it's actually going to happen in a lot of cases where you're dealing with orthogonal estimating equations. And you're always going to have this condition which allows this very convenient reformulation of the problem. So in fact, what we show in the paper is that if your estimating equation satisfies an orthogonality condition with respect to the nuisance eta 1, with respect to a Frechet derivative, then the invariant Jacobian assumption is satisfied. So essentially what this is just the Niemann orthogonality condition, just with respect to the eta 1 nuisance, but using a Frechet derivative instead of a Gateau derivative, which is what's used in the Niemann orthogonality conditions in DML and the earlier papers. So if you remember a little bit of your analysis, Frechet derivatives are generally stronger than Gateau derivatives. So this is slightly stronger, but it turns out that it holds almost everywhere. It holds for all of the examples I mentioned before, thanks to double robustness. So why are all of these doubly robust estimating equations even orthogonal? They're orthogonal because once we plug in one correct nuisance, they don't depend on the other nuisance. They're correct. So if, for example, we consider this estimating equation and we plug in the correct eta 2 nuisance, so for example, for QTEs, this would be the correct propensity. Well, now this is the actual CDF minus gamma. It doesn't depend on eta 1 anymore. So in particular, it has a 0 derivative with respect to eta 1, a Frechet derivative, because it doesn't even depend on eta 1. So it has a very good derivative. And 0 is, of course, orthogonal to everything. So we satisfy the condition, and we have invariant Jacobian assumption. So now we have an alternative moment condition to target this moment condition. So now what we're going to propose is an alternative algorithm to target this alternative formulation. And that's going to lead us to the LDML algorithm, the Localized Debiased Machine Learning algorithm. So we're going to take all of our data and we're going to split it into k even folds. And k is some fixed number. And then for each little k from 1 to capital K, we're going to do the following. We're going to look at all the data that is not in the kth fold, okay, so the complement of the kth fold, and we're going to split that in turn into two halves, complement 1 and complement 2. Complement 1 and complement 2. Then we're going to use only the data in complement 1 to construct an initial guess for theta. So for an example in problems like QTE, we're going to use the IPW estimate of theta using just the data in complement 1. Then we're going to use complement 2 to construct an estimator of the estimand dependent nuisances, eta 1, at the specific value of the initial guess that we just fit. So instead of fitting this for all possible theta, we're only estimating it for this one particular theta. And this particular theta is fixed with respect to the data that we're using. So this looks like estimating a single nuisance, or in the case of QTE, just like estimating a single binary regression. Finally, we're going to use the whole complement to construct an estimator for eta 2. And then what we're going to do is we're going to plug this in and solve for theta, right? So we're going to look over all the data I, and we're going to evaluate psi at zi. But when we do that, we're going to use the estimand, the nuisance estimators, eta 1 hat and eta 2 hat, that were fit on the complement of the fold that contains I. So on the complement of dk. And then we're going to take the average over all the data and look for the theta that minimizes that solves this least squares problem, or maybe solves it up to some vanishing error. And that's it. That's the estimator. So just to show this in another way, let me give you this in a schematic kind of representation. So this is a representation of one run of the for loop. So for k, little k equals to 1. So we want to evaluate psi at some zi that's in the first fold. So we're going to take fold 2 and 3. And from these two, we're going to construct an estimator theta hat init, some initial guess for theta. From the 4th and 5th fold, we're going to estimate eta 1 hat at this particular value of theta. We're going to use folds 2 through 5 to estimate eta 2. And then we're going to plug all of these into psi in order to get psi at zi. We're going to do these for all the I in the first fold. And then we're going to exchange the roles of the folds. So we're going to do this for little k equals 2, little k equals 3, little k equals 4, little k equals 5, and average everything. And as an example, what can we do to get an initial guess? Well, we can do a cross-fold estimated IPW. So we can take, for example, if we focus on just this part of using D2, D3 to get theta hat init, we can, for example, use D2 to get an estimate for the propensities, use D3 to get another estimate for the propensities, plug each of those in a cross-fold way, average it, solve for theta, and get an initial guess. So if we put everything together, we get this complicated schematic, but this does everything just right so that we get the right type of behavior that we can have guarantees for the estimates that we get if we just use black box plugins, which is something Xiaojie will talk about. I just want to mention briefly that this was just an algorithm for estimation, but we can also desire some inference on these target parameters. Well, we said we're going to be asymptotically normal, so all we need is the asymptotic variance to conduct inference. So in the paper, we propose a variance estimator, which again is estimated using these cross-fold things, where for each unit I, you're going to use the cross-fold estimated nuisances. And you can use these to construct confidence intervals with exact asymptotic coverage. And just one note is you only need, in this LDML procedure, we started by randomly splitting the data. So you actually only need just one random split. That's enough to ensure the desirable asymptotics that Xiaojie will talk about. However, this, in a finite sample sense, is just unnecessary noise. In theory, we want to average over this, right? And average over all possible splits. In practice, what we recommend to do is to just run several iterations of LDML and then take a median or winsorized mean of the estimates. And this is going to make sure that we're not being badly affected by bad luck of getting a bad split that's giving us an outlier. And you can also use this to expand the standard errors to account for averaging over the iterations of LDML, but this is not necessary. This is like not something that comes into the asymptotic variance. So that's the method. First you localize, and then you essentially do a DML type thing with a 3-way split of the data instead of just a 2-way split in its simplest form to localize it, I guess, and estimate the estimate-independent nuisances only at that guess. So next, I'm going to turn it to Xiaojie, who's going to tell us more about what we can say about this method theoretically, and give us some empirical results, and then conclude. So Michael, can you help me transfer the presentation to Xiaojie?
And then maybe before we transfer, I think Dominic had a question.
Yeah, just a quick question. So I guess you make an assumption, I might have missed it, but you probably make an assumption somewhere that the density of Y is smooth. Or what happens if you have probability map?
Yeah, so we're gonna, that's exactly right. So when I said in the beginning, assume unique, essentially what I was hiding, which is something that's formal in our assumptions, is that it has a density at the quantile.
Okay, and just
so that's absolutely there, and that's going to make sure that everything is regular.
Yeah, thanks. And if that's not the case, did you try in simulation? What happens basically? Do you still kind of get reasonable results?
So we didn't try that in simulation. That's a really good suggestion. Yeah, we'll try that.
Okay, Xiaojie, okay, good.
So can you see my screen?
Yeah, maybe if you want to make the slides full screen. Yeah, there you go. That's good.
Okay, cool. All right, thanks Nathan for introducing the method. Now let me continue talking about the asymptotic guarantees. First let me still talk about quantile treatment effect. And as Nathan already mentioned, we want to do the estimation based on the efficient estimation equation, which is basically a augmented IPW estimation equation like this, which involves two different nuisance parameters. And the first one is the propensity score, which we assume to be bounded away from 0 by a constant epsilon. And we also have another nuisance mu star, which is this conditional CDF function, at the true quantile that we want to estimate. So that's why we want to use this localization strategy, and we localize our conditional CDF estimator only at this initial guess of the quantile, and also estimate the propensity score, and then form this sample analog of the estimation equation in order to get to the final LDML estimator for the gamma quantile of Y1. And in order to ensure that our estimator has good property, here we first specify the convergence rates of the nuisance estimators. So we assume that with the probability approaching to 1, for all of the nuisance estimators, we assume that the convergence rates of estimating the conditional CDF at this initial guess, and also estimating the propensity score, and also estimating, and also the convergence rate of this initial guess are, rho mu n, rho pi n, and rho theta n respectively. And because in the estimation equation, we need to use this inverse propensity score weight. So here we also assume that the inverse estimated propensity score is upper bounded, so that our estimator is well defined. And moreover, we also need some regularity conditions on the data generating process. So here we assume that the true quantile is in the interior of a compact parameter space theta, and we assume that for any theta within this space, the marginal CDF function of this Y1 is twice differentiable with the density that's upper bounded and also lower bounded away from 0. And we also assume that second order derivative is bounded. And we assume a similar condition on the conditional CDF function and also its first two derivatives. So here actually we can actually relax this condition a bit. Actually we only need to require that the density at a true quantile is bounded away from 0, but at expense of introducing some actual technical conditions. But here for simplicity, let me just focus on this stronger setting. So we can show that with all of these assumptions, if we further assume that all of these nuisance can be estimated consistently, so all of their rates are neta 01, and also we assume that the product of the convergence rate for estimating the propensity score and the convergence rate of estimating the conditional CDF localized at the initial guess, and also the initial guess estimator is faster than square root n, then we can show that our localized Debiased machine learning estimator for the quantile is asymptotically linear, and obviously it's also asymptotically normal, and this asymptotic variance is actually the semi-parametric efficiency lower bound, because we use the efficient estimation equation. So our estimator is also asymptotically efficient. So in our paper, actually we have stronger results than this, because we take care of all of the constants pretty carefully. So this asymptotic linear expansion also holds uniformly over a instance class, not just for a single instance. And here, back to what Nathan mentioned before, here I want to say that our analysis is somewhat different from the analysis in Chernyshkov et al. In 2018. And because if for nonlinear estimation equation, if we use their analysis directly, then we would need to assume that all of the convergence rates for all the nuisance parameters are faster than 40 root of n. But here, because we use our new analysis, we only need to assume this square root n condition on the product of the convergence rates for estimating this nuisance, instead of a rate condition on each individual nuisance parameter. So this is really nice because it allows us to sort of trade off the convergence rates for different nuisance estimation. If we want to estimate the QTE, then we just estimate two quantiles for two potential outcomes respectively, and then take the difference. And we can show that this QTE estimator also inherits all of the good properties of each marginal quantile estimator. Also, as Nathan already mentioned, a natural candidate estimator for this initial guess for quantile is this IPW initial estimator. And because we only use propensity score here, we don't have the orthogonality condition. So usually the estimation, the conversion rate for this initial guess has to be upper bounded by the conversion rate of the propensity score estimator. And in this case, if we want to satisfy this condition, then we have to assume that the propensity score is estimated at a rate that's faster than fourth root of n. And even in this case, even though we require it to be faster than fourth root n, because we only require this product rate condition. So if we can estimate the propensity score at a faster rate, then we only need to estimate the condition CDF at a relatively slow rate in order to satisfy this condition. And in order to the inference, we need to estimate the asymptotic variance. And here we have that J star term, which is basically the density at a true quantile. And in order to estimate that, a natural candidate is to use this IPW kernel density estimator. But usually it might not be that stable because of some propensity score estimates that might be close to 0, 1. So in this case, we may consider using self-normalization to stabilize the estimator or just knip some extreme weights. So with all of these ingredients, then we can construct the asymptotic variance estimator pretty easily by using this plugin estimator, and then also construct the confidence interval. And we can show that under all of our assumptions, if this density estimator is consistent for the true density at a true quantile, then our confidence interval is also asymptotically valid. So this is the basic results for our QTE estimation. But of course, we made one assumption there. That is, we have the unconfounded assumption, which might not really hold in practice, especially for observation data. And if that is violated, then one common solution is to use the instrument variable. And in this case, we consider, for example, the most common and basic setting where we have a binary instrument variable W, and we also have a binary treatment variable T. And we assume all of the standard IV assumptions. And here, our goal is to estimate the local gamma quantile of the this theta star parameter that is basically defined by the quantile of the distribution of Y1 for the compliers or individuals who choose their treatment status by following the instrument variable value.
Xiaojie?
So in order to estimate,
so can you wrap up in 5 to 7 minutes or so? Okay,
sure. So in order to estimate this, we still use the efficient estimation equation that's also mentioned in study in Alex's paper before. And here, we also have some nuisance, like the mu tilde star here, which is also some sort of conditional CDF type of nuisance. And again, we can use our localization strategy to solve this, because we can also show that this efficient estimation equation also satisfies the orthogonality condition. So again, we just estimate all of the nuisance and plug them back into the estimation equation and solve this sample analog to get our final LDML estimator for local quantiles. So here we have one actual nuisance that I didn't really take much time to talk about its meaning, but it's basically estimating the the average causal effect of the instrument variable on the treatment variable. And in order to estimate that, actually we only needed it to be consistent in order to ensure the nice theoretical guarantees. There are many choices for that, and I think in Alex paper they use like a W robust estimator for that, so we can definitely use that. And also we can show that under very similar conditions for QTE, we can also show that this LDML estimator for local quantile tripling effect estimator is also asymptotically normal, is asymptotically linear, and also efficient. And we can also construct confidence intervals that are asymptotically valid in a similar way. So besides the quantiles and also the local quantiles, we actually also have a general theory for solving, for using localized debiased machine learning for estimation and inference with a generic nonlinear orthogonal estimation equation that involves some nuisance that depends on the estimand itself. And we only need this orthogonality condition and also generic rate conditions for nuisance estimation. And we already presented one example, two examples. The first one is the QTE estimation, and we can actually consider more general parameters defined by some estimation equation for the potential outcomes. And under the unconfounded assumption, we can show that it is pretty well known that the efficient estimation equation satisfies this orthogonality condition. And another example is like a generalization for local quantile tripling effect, where we can consider this sort of IV setting where the estimation equation is defined for the compiler population. And again, the efficient estimation equation would satisfy the orthogonality condition. So in this way, our framework provides a pretty generic and unified recipe for solving a large family of problems that's common in causal inference and the missing data kind of problems. All right, so let me speed up a little bit for the empirics part. So here, basically we consider estimating the local quantile tripling effect using a pretty classic example about the effects of 401k participation on people's net assets. And here, this tripling variable participation might be confounded with wealth. So previous studies considered using the 401k eligibility as an instrument for that. And in previous studies, like Chirchikov and Hansen considered like a no-dimensional linear models. And then Alex paper, extends that and include more high-order interaction terms in order to make the model more flexible. But again, they need to estimate many Nusselts on a discretized grade of thetas. And also their results are kind of specific to Nusselts. And then later on, Chirchikov et al. Extend this idea to generic black box methods, but in their empirical study, they only tackled averages. And here we consider using like localized debiased machine learning to do inference and also estimation for QTE and LQTE using a variety of black box regression methods. So for the interest of time, let me only show you one result here. So here we estimated local quantile tripling effect corresponding to different quantile levels using our estimator, where we estimate the nuisance by using different types of estimators like Nussel, neural nets, and boosting. And we also use a different number of folds in cross-fitting. So these are the estimates. And we can see that when we use, the estimates are pretty stable across different number of folds. And also when we change the nuisance estimators, the results are roughly similar, which kind of shows the robustness of our method, even though we only target, our nuisance at a single point. And also we have some plots here about the, the whole curve for the local quantile tripling effect. So the punchline here, I think, is that the results are actually pretty similar to Alex paper's results, but here, arguably, our estimator is much simpler to implement, and at the same time, this result also shows that and this is for this example, quantile tripling effect is like a pretty informative measure because it indeed reveals these variations of the causal effect over different quantile levels. All right, so we also have some actual results for QTE estimation. But for the interest of time, let me just skip them here because their patterns are kind of very similar. So finally, let me conclude our talk here. So here we consider estimating the QTE and also LQTE that are quite important in empirical studies, especially when the outcome distribution can be skewed. And these quantities are kind of more difficult to estimate especially if you have like a high dimensional covariance or some other complex settings. And the state-of-art DML method requires us to estimate a whole continuum of nuisance, which might be quite challenging, especially that it doesn't fit into the usual supervised learning framework in ML pretty well. And then we propose to use this localization approach to localize the nuisance estimation only at a single point based on a rough initial guess. And our estimator can still achieve the asymptotical behavior that's like the oracle estimation using the true nuisance on the only generic conditions for the black box regression methods for the nuisance estimation. And we do not need to fit many nuisance. We do not need to use some ad hoc discretization approach, which might be sort of more easier to implement in practice. And we also have more general theory about any sort of nonlinear orthogonal estimation equation whenever the nuisance might depend on the estimator itself. And here we basically need a slightly stronger Fréchet derivative orthogonality condition, which is actually specified for a large family of problems in causal inference and the missing data problems. So I guess that's all I want to talk about today. So thank you so much for listening.
Fantastic. Thank you, Xiaojie and Nathan, for the great talk and presenting your work here. We're now switching over to the discussion. So we will have Alexandre Belloni, and after that, Nathan and Xiaojie can respond. So I'm now switching over to you, Alexandre, so you can unmute yourself. Yeah.
And to share my screen. So first, I'd like to thank you for the very, Nathan, Xiaojie, for the very good presentation. It was a pleasure to read, to go over the paper. So in a nutshell, right, the goal of the paper wants to estimate, propose some efficient inference, right, in the presence of these high dimension nuisance parameters. So we can actually blend all these nice machine learning tools and still produce these asymptotically valid confidence intervals that we like to measure impact. So it has been motivated by causal effect estimation. There are plenty of applications, but it's certainly applicable to any other setting. So it's a very nice framework, pretty much aligned with the work of double machine learning that, yes, has a great applications in causal inference, but it's also good in other settings. And right, so the idea, we have this IID data, we have some parameter of interest we like to estimate, and the main challenge are to handle the nuisance parameters that are high dimensional. And as Nathan made a very good case, and has been tested over and over, the orthogonal moment conditions have been incredibly useful to make this blend between causal inference and machine learning. That's kind of the really what open up this intrinsic bias for machine learning methods that would, by design, kill any hope of building confidence intervals. Orthogonal moment conditions really open up this nice path to do it. And this is by no means new, right? This has been, there's a huge literature going back to, of course, Niemann in the 50s that motivated these orthogonal moment conditions to reduce the influence of nuisance parameters. And same parametric and non-parametric estimations have been used a lot in statistical econometrics. And more recently, it's really the push towards machine learning was done in several papers that have been incorporating these insights. But it's really a huge literature. I do want to apologize for many issues that are happening here. And right, there was the double machine learning that was a nice, double machine learning was a nice way to apply these with sample splitting that has been extremely well received and has for good reason. And there are even more omissions after that came and have been applying this. So in the paper, right, a key issue is that one of these nuisance parameters, right, it depends precisely on what we want to estimate, right? So that poses some challenges, as Anita described. But then again, what makes it possible to achieve is the fact that since if we are using these orthogonal moment conditions, the dependence on the nuisance parameter itself is going to be small in a local neighborhood, as long as we have a rough estimate of this initial point, we can replace with this estimator. If the dependence of this function is smooth with respect to your estimator, then you are in business again, right? So that's a very, he found very nice examples where you can use this initial crude estimators for this theta, and here should be a theta, apologies. And then you are in business and you can proceed to estimate. They also provide a very nice explicit data splitting procedure to account for this initial estimator that you have. And this really brings you close to black box regression methods in machine learning, which you want to leverage, right? So you want to be able to use all the tools that are available and these constructive schemes that are going to combine and push you further. So this is kind of in a nutshell, and I know I don't have much time, but so let me really emphasize that the assumption that Nathan explicitly wrote of the J diamond being equal to J star, right? It really holds quite generally, and it's an important takeaway of the talk, because what he's saying is that in the nuisance function space definition, you can play a lot. So if there's any overlap with the auto parameters you want to estimate, you can redefine them in different ways. So you can choose very different nuisance functions, so you can try to take advantage of the estimation procedure in different ways. So for example, it could simplify computation. If you can plug in crude estimates there, that will not feed back in your loop. So that there are, you have an extra degree of freedom there that you want to take advantage when you are designing your estimation equation. And this has showed up in other places, right? Especially when you do with multivariate parameters. Like if theta 1 has many components, it's very natural to think that one of the components influences the other one and vice versa, and you care about all of them, right? So there is some spirit that your nuisance functions are depending on your on the actual parameters you want to estimate later on. And at the same time, you can also think about iterative schemes, right? Once you estimate you get first estimators, you could plug back. Once you get these Debiased estimator, you can plug back them into the nuisance functions themselves and see how this iteration goes. Now, what happens is we have all this freedom, and it all is first order asymptotics is the same. So it doesn't really matter from the first order asymptotics, right? What is interesting to investigate further is there any choice that has an impact on higher order asymptotics? Right? So when you're doing these decisions to gain computation, are you giving up something in terms of higher order asymptotics that could be important in your setting? So this is, I think it's does not belong in this paper. It's just a potential question. If the authors have a comment on that, it would be interesting. So yes, so I remember I read a few times this continuum of Lasso that showed up in this earlier paper. Right? It is, to some extent, is a way to to be able to achieve a first rough estimator in the process. And so let me just comment that you don't need to solve a continuum of lasso because you only observe a finite number of values. So anything between those is the same. So it's not a continuum, but that's a separate point. But the question would be, right, so it's really about this initial estimator, right? So if you can comment a little bit how general you would be on that aspect in terms of initial estimator would be good. It seems that you have, again, as the double machine learning tool framework, you have a very nice connect with high-dimensional central limit theorems. So just want to touch there if you can comment on that. And then there is one technical question you don't need to answer now, just to take offline, given the time, is about equation 20 in the paper on the remark that has some dependence that I might be missing something, but this is less important than the other ones. So I might be a little bit over time, but especially if you could give me some comments potentially on the higher order asymptotics, if you have any views there, would be great.
Thanks for the nice discussion, Alexandre. Nathan, Xiaojie, do you want to respond?
So I guess I can respond a little bit on the technical condition about the equation 20 and also on the high order asymptotics. So first of all, for the equation 20, so this is actually all a bit mystic because we were putting things together, sort of last minute. So actually in the latest version, which we updated yesterday, this mistake was already fixed. So here, we actually don't really need this, this quadratic moment, this square moment to be upper bounded by the, the square of the distance between theta and theta star. We actually only need that to be continuous. We only need the exponent to be, for example, an arbitrary delta that's larger than 0. It doesn't need to be 2 in order to ensure the whole conclusion holds. Because here, the whole reason why we have this kind of technical conditions because we want to ensure that I think our asymptotic variance estimator is valid so that we can do inference. So in that case, we only need consistency. We don't really need like a, sort of rate control. So here we don't really need like a quadratic upper bound. So for example, for the bounding in the last line, we might use like a absolute value rather than the square root of theta 1 minus theta 1 star.
Okay, sounds good.
Yeah, and for the high order asymptotics, I think that's really an interesting question. We don't really think much on that, I think, because currently, when we control the influence of the estimated, the influence of using the initial estimator, it's bounded in somewhat a pretty crude way. In that way, you use, the continuity of the sort of a Lipschitz continuity of the nuisance with respect to theta. So, that crude analysis really probably won't give us much information about its impact on like high order asymptotics, etc. But I think this is a really, really interesting question that is worth exploring, especially given your comments on how we can, sort of play around with all of this nuisance and view them in different ways. It's really interesting to see like how, what's the trade-off of using like different estimators. Like how we view the nuisance parameters. So yeah, I don't really have an answer for that, but I just want to see that I really appreciate this question.
Thanks. Nathan, do you also want to add something?
No, I don't have an answer to that question either. I also think it's interesting, but I think it's just I think it's beyond the analysis right now. But I want to say thank you to Alex and thank you for two really good catches, like a mistake that we found as well. And that you're right, it's not a continuum. You only have to do capital N lassos. That's true.
I did not expect an answer for the high order asymptotic.
Yeah.
Right. It's just
no, but it's a good point to put out there.
And even simulations might start to review if there is anything there. Right. So
but even in simulations, it's hard to see
second
order behavior. I mean, you have to do like really large simulations.
It's about the design, right? Yeah, about finding a design in which it would matter. But there is plenty of work on higher order asymptotics, so they can make an impact.
Absolutely.
All right, great. Thank you all. I think it's now slowly time to wrap up. So first, thank you all for volunteering today. So 1 second. So thank you, Nathan and Xiaojie, for volunteering to speak today. It was a very nice presentation. Thanks, Alexandre, for a great discussion. Also, thanks to Masatoshi for helping out in Q&A today. All right. Yeah, and last but not least, thank you all for joining. Next time, we have two speakers. We have Falco Bargagli-Stoffi, who will talk about causal rule ensemble interpretable inference for heterogeneous treatment effects. And we have Eli Ben-Michael from UC Berkeley, who will talk about synthetic controls with staggered adoption. So we're really looking forward towards that talk. Hope to see you all there, and we hope you all stay safe until then. Thank you all for joining. See you soon.
Great job, guys. Thanks.